Welcome to the Deep Dive, your destination for really getting under the hood of complex subjects. Today, we're tackling something pretty fundamental in data analysis. It's this reality that, well, the world doesn't often move in perfectly straight lines, does it?
Not usually, no.
We tend to default to linear models. I mean, they're simple, they're easy to explain, but, what happens when that simple straight line just isn't cutting it? When it's not really telling the full story?
That's the core question, isn't it?
Exactly. So our mission in this deep dive is to explore some powerful ways to move beyond just linearity. We want to help you capture those true, often kind of curvy relationships that might be hiding in your data. We'll get into things like polynomials, those are the curvy classics, and then look at step functions, which are more blocky but really clear. And then things get really interesting with concepts like splines. Think of them as flexible, smooth curves, and something called GAMs, generalized additive models, which let us combine lots of these flexible shapes. Basically, if you've ever looked at a data set and thought, a straight line just feels wrong here, then this deep dive is definitely for you.
It's so true. I mean, think about it. Nonlinear relationships are just everywhere in the real world. Natural processes, economic stuff, even how people behave over time. It's rare that things change at a perfectly constant rate.
Right.
And while linear models they're crucial, they're the foundation for so much, understanding where they fall short is really the key to getting more accurate and, then, frankly, more honest predictions. Having that toolkit to model the curves and the sudden shifts, it's not just about adding complexity for its own sake. It's really about getting closer to what the data is actually trying to tell us.
Yeah, the underlying truth.
Exactly. And just for context, a lot of our discussion today is inspired by the great work in An Introduction to Statistical Learning. It's the kind of material that forms the basis for courses like, say, MGMT 47400.
Okay, so we get it. The world is messy, non-linear. But let's really pinpoint the problem. Why can't we just always use straight lines? What are we actually missing or, getting wrong when we do that?
That's a really important point. As the book puts it quite bluntly, the truth is never linear, or almost never.
Okay. Pretty clear.
Yeah. And when you force a linear model onto data that isn't linear, you run into, well, mainly two big issues. First, your predictions might just be consistently off in certain areas, leading to bad forecasts. Second, and maybe even more critical, you could totally miss important patterns or insights.
Like what kind of insights?
Well, imagine trying to model, say, income based on age. It's definitely not a straight line that goes up forever, right?
Right. No, it usually peaks somewhere.
Exactly. It often peaks, maybe it plateaus, maybe it even declines later on. If you just fit a straight line through all that, you miss the peak earning years, you miss the flattening out. You basically just smooth over the actual story.
It's like trying to trace a mountain range with just a ruler, isn't it? You'd completely miss the peaks and valleys.
Perfect analogy. Yeah, it might be good enough sometimes, but you're leaving so much detail, so much reality on the table.
Okay. So we need something more flexible.
We do. And embracing these nonlinear methods gives us that flexibility. We can build models that actually follow the shape of the data better. And the really clever part about the techniques we're discussing is they give you this flexibility without totally sacrificing the interpretability we like about linear models. We're not just building black boxes here. We're building, let's say, more finely tuned lenses to see the data.
Okay, lenses. I like that. So let's start looking through these lenses. First up, polynomial regression. You called it the curvy classic. What's interesting here is how it kind of twists linear regression to get those curves.
It's a really smart first step, yeah. Instead of just using your predictor, let's call it x, you also add powers of x as predictors. So x squared, x cubed, x to the fourth, and so on.
Okay.
So if we're predicting, say, wage using age, a fourth degree polynomial would look something like wage equals some intercept plus a coefficient times age plus another coefficient times age squared plus another times age cubed and one more for age to the fourth plus some error.
So y equals 1/9 plus OA egg plus 2/2i plus 3/3i plus 4/4i's plus IA, something like that.
Exactly that.
Now, it sounds a bit weird because the output is curvy, but you mentioned the model is still linear in the coefficients, the betas. What's the practical upshot of that? Why is that good?
That's a really crucial point. Because it's linear in the coefficients, we can still use the same fundamental math, the same least squares methods that we use for standard linear regression to find the best beta values.
Okay, so we don't need totally new tools.
Right. It makes polynomial regression a very accessible bridge, kind of, from the linear world to the nonlinear one. Often, we're less focused on interpreting each individual beta coefficient here.
Right, like what does beta 3 mean?
Exactly. It gets complicated fast.
Yeah.
We're usually more interested in the overall shape of the curve that those fitted values produce. But, and this is a big but, this method does come with a pretty well-known issue, what's called notorious tail behavior.
Notorious tail behavior. Okay, that sounds like something we need to watch out for. What does that mean if I'm trying to make predictions?
It means that your predictions way out at the ends of your data range, the tails, can get really wild and unreliable.
Oh.
See, polynomial regression has a global effect. A weird point or just sparse data at one end can actually pull the whole curve out of shape, even far away from that point.
So it's not very localized.
Not at all. It makes it hard to trust predictions beyond the main range of your data. Like in that wage example, if you only have a few people over age 70, the model's curve out there might shoot up or down unexpectedly. The uncertainty, the standard errors tend to blow up where data is thin. That's related to something called leverage.
Okay, so be careful at the edges. How do you even choose how many powers to add? Like x squared, x cubed. How high do you go?
Good question. That's choosing the degree, D. You could just fix it at something relatively low, maybe 3 or 4 often works okay. Or a more data-driven way is to use techniques like cross-validation to see which degree gives the best predictive performance.
Right, let the data decide.
Yeah, and it's worth noting, you can use this polynomial idea in logistic regression too for modeling probabilities in a nonlinear way.
Okay, interesting. So from these smooth, sometimes globally influenced, maybe a bit wild at the ends curves of polynomials, let's switch gears completely. Step functions. If polynomials are like drawing a smooth line, you said step functions are like building with Legos, distinct flat pieces.
Yeah, that's a good way to put it. It's a really different philosophy. The idea is super simple. You just chop up the range of your variable into, say, k different regions or bins.
Okay.
And for each region, you create a dummy variable. It's 1 if your data point falls in that region, and 0 otherwise. So you might have one dummy for, say, age 35, another for 35 equals age 50, and so on. The result is what we call a piecewise constant function. It's flat within each piece.
Right, flat steps. That sounds simple. What's the main advantage of doing it that way?
The big win here is what we call local control. This is the exact opposite of polynomials. With step functions, changing the fit in one interval one step has basically 0 effect on the other intervals.
Completely separate.
Totally separate. This makes them really straightforward to understand and interpret, especially if your data actually has natural breakpoints, maybe a policy change at a certain income level, or there are distinct phases in a process.
Like different life stages for the age example.
Exactly. And they're also great for creating simple interactions. You could have like an interaction between age and an indicator for year 2005 that lets you fit different relationships before and after 2005, for instance.
Okay, but the trade-off must be that blocky look, right? It jumps suddenly. It's not smooth.
That's the main drawback, yeah. The fitted line isn't smooth, which might not feel right for a lot of real-world things that change gradually. And critically, you have to decide where to put those cuts, those knots.
That sounds tricky.
It can be. Choosing the cut points is a really important decision. I remember working on a project, looking at customer behavior, and just shifting one cut point by a little bit completely changed how we thought about different segments. It showed just how sensitive the model can be to those choices and how, well, subjective it can feel sometimes.
So simple, interpretable, good local control, but maybe looks unnatural and depends heavily on where you place those cuts.
You got it. It's a trade-off.
Okay, moving on then. It feels like there should be a way to get the best of both worlds, the flexibility, but maybe smoother than steps. That brings us to regression splines.
Yes, splines. This is where things get really elegant, I think. They cleverly combine ideas from both polynomials and step functions.
How so?
Well, like step functions, they start by dividing the range of the predictor into different regions using these points called knots.
Okay, knots again.
Knots again. But here's the magic. Instead of fitting a constant value in each region, splines fit different polynomial functions within each region.
So curves within each section.
Exactly. But the really crucial part, the thing that makes them splines, is that these polynomial pieces are forced, they're constrained, so that they join up smoothly at the knots.
Smoothly. How smoothly?
That's the key. Our source material has some great visualizations. You can imagine just forcing the polynomial pieces to meet at the knot. That gives you continuity. But you can go further. You can force their slopes to match the knot that's continuous first derivative. And you can even force their curvature to match continuous second derivative. Splines usually aim for that higher level of smoothness.
So it looks and feels like one continuous flowing curve, even though it's made of different pieces.
Precisely. That's the goal. Let's break down the simplest type first. Linear splines. These are piecewise linear, like connect the dots, but they are continuous at the knots. We build them using basis functions. A common way is to have one function that's just x itself. Then for each knot, let's say at position room, that's ice k, you add a function like xak plus...
Xak plus, what's the plus mean?
Good question. The plus means the positive part. So xak plus is equal to xxk if x is greater than the knot xk, but it's just 0 if x is less than the knot. It only kicks in after the knot.
Okay, so it adds a change after the knot. Can we do a quick example?
Sure. Let's go back to wage versus age. Imagine we put just one knot at age 50. The model might look like wage equals 0 plus O1, age plus CO2, age 50 plus the egg.
Okay.
Now, for anyone age 50 or less, that age 50 plus term is 0. So the slope is just Liade 1.
Right.
But for someone older than 50, the age 50 plus term becomes age 50. So now the slope is effectively Liebel 1 plus free 2. The line is continuous at age 50, but its slope can change there.
So you get a kink in the line, but it's connected.
Exactly. A hinge. This gives you local flexibility. The slope can change and it's continuous. And importantly, unlike those global polynomials, what happens before age 50 doesn't unduly distort what happens after 50, and vice versa.
That seems much better behaved than the polynomial tails.
Generally, yes. Now, we can go smoother than just linear pieces. Cubic splines are very popular. These fit piecewise cubic polynomials between the knots.
The cubics, okay, so curvier pieces.
Right. And they're constrained to be continuous not just in value, but also in their first and second derivatives at the knots. This makes the resulting curve look very smooth to the eye.
That sounds really useful.
It is. And there's a further refinement called natural cubic splines. These add a couple of extra constraints, basically forcing the function to be linear beyond the boundary knots, the very first and very last knots.
Why do that?
It helps prevent weird, erratic behavior way out at the extremes of your data where you might have fewer points. It makes the extrapolation more stable and less prone to overfitting in those sparse regions.
Okay, that makes sense. So with splines, we still have knots. How do we choose where to put them? Is it subjective, like with step functions?
It can be, but there are common strategies. Often, you first decide how many knots you want, let's say k. Then, a sensible approach is to place them at specific quantiles of your predictor variable x. For instance, put them at the 25th, 50th, and 75th percentiles to ensure they're spread reasonably across your data.
So let the data guide the knot placement too.
Yeah, it's generally better than just guessing. And just quickly, the number of knots affects the model's flexibility, its degrees of freedom. A cubic spline with k knots uses k plus 4 degrees of freedom. A natural cubic spline is a bit more constrained, using k degrees of freedom.
Got it. Okay, splines seem powerful piecewise polynomials, joined smoothly. But choosing knots still feels like a bit of an art. Is there a way to make it more automatic?
Ah, you've anticipated the next step perfectly. That leads us to smoothing splines. These take the spline idea and add, as you said, a layer of mathematical automation to handle the knots.
Okay, I'm intrigued. How do they automate it?
What's really wild about smoothing splines is this. Instead of you picking a few knots, they essentially place a knot at every single unique data point in Pullen.
Wait, every point. Wouldn't that just connect all the dots perfectly and overfit like crazy? That sounds disastrous.
It would be disastrous if that was all there was to it. But that's where the clever math comes in. Smoothing splines don't just try to fit the data perfectly. They solve an optimizing problem. They try to minimize a combination of two things.
Okay, what two things?
First is the usual suspect, the residual sum of squares.
Yeah.
So that measures how closely the function gx fits the data point to you. It wants to minimize errors.
Standard stuff. What's the second part?
The second part is a penalty term, dot dt. Now, g is the second derivative of the function, which measures its curvature or wiggliness. Squaring it and integrating basically measures the total amount of wiggliness over the whole function.
So it's balancing, fitting the data against being too wiggly.
Exactly. It's a tug of war.
Okay.
Fit the data well, low RSS, but keep the function smooth, low penalty. And that parameter lambda controls the trade-off.
Lambda again. So what does lambda do?
Lambda is the smoothing parameter. It's crucial. If UC is 0, there's no penalty for wiggliness, so the function will likely wiggle a lot to hit every single data point, massive overfitting.
Okay.
If UC is huge, approaching infinity, the penalty completely dominates. The function is forced to be incredibly smooth to minimize the penalty, so smooth it becomes just a straight line. The least squares line, in fact.
Yeah. Wow, okay. So lambda dials the flexibility from wiggly interpolation all the way down to a straight line.
Precisely. It controls that balance between bias over smoothing and variance over fitting. Now, choosing directly can be tricky. A really neat feature is that you can often specify the desired effective degrees of freedom d-phi instead.
Degrees of freedom, like in linear models.
Sort of analogous, yeah. It gives you a more intuitive handle on how complex, how flexible the resulting curve is. Specifying d-phi, for example, gives you a curve with roughly the flexibility of a polynomial of degree 4 or a spline with a certain number of knots.
That sounds easier than picking a raw lambda value.
It often is. And even better, there's a very powerful data-driven way to choose R or d-phi automatically, using leave-one-out cross-validation, LOACV.
Ah, cross-validation. We like that.
Yes, you can calculate the cross-validated RSS, often written RSSCV for different values of R, and pick the U that minimizes this prediction error on unseen data. It's computationally efficient for smoothing splines and helps ensure your chosen smoothness level generalizes well.
So smoothing splines automate not placement, but putting them everywhere, but control the resulting complexity with a mathematically elegant penalty term, often tuned via cross-validation.
That's a perfect summary.
Okay, before we tie this all together with the grand synthesizer, GAMS, there's one more technique worth mentioning quickly. Local regression. How does this fit in?
Yeah, local regression, sometimes called OLOS or LOES. It's another approach to flexible fitting. The key difference from splines is that while splines define distinct regions between knots, local regression uses regions that sort of overlap smoothly.
Overlapping regions. How does that work?
Basically, to make a prediction at a specific point, say x0, local regression fits a simple model, often just a local linear regression, using only the data points near x0. Points closer to max0 get more weight in this local fit, and points further away get less weight, often using a smooth weighting function, like a little bell curve centered at x0.
So it's like focusing a spotlight, fitting lots of little local lines.
That's a great way to think about it. You slide that spotlight, that weighting function, across the range of x, and piece together the predictions from each local fit. The result is often a very smooth curve that adapts well to changes in the data's behavior locally.
Okay, so another way to get smooth, adaptive curves, focusing on local neighborhoods rather than fixed knots.
Exactly. It's particularly useful when the relationship's complexity varies a lot across the range of the predictor.
Right. Now, bringing this all home, we've looked at polynomials, steps, various kinds of splines, smoothing splines, local regression. These are all great for modeling the relationship with one predictor. But what if we have multiple predictors, like in most real-world problems? Does all this nonlinear goodness go out the window?
Absolutely not. And that's where generalized additive models, or GAMs, come into play. They are the grand synthesizer, as you call them.
Okay, so what do GAMs do?
GAMs provide a framework to extend all these nonlinear techniques to handle multiple predictors at the same time, while, crucially, maintaining a structure that's still relatively easy to interpret.
How do they keep it interpretable with all that flexibility?
They retain the additive structure of linear models. A GAM looks like this. The response y equals an intercept yarrow plus a smooth function of the first predictor f1 by I1 plus a smooth function of the second predictor f2 by I2 and so on for all p predictors plus error. Y equals 0 plus f1 by I1 plus an f2 by I2 plus fpe plus y.
Ah, so each predictor gets its own smooth function, f, and then you just add their effects up.
Precisely. That additivity is key. It means you can examine the estimated shape of each function f1, f2, etc. individually to understand how each predictor relates to the response, holding the others constant.
And those f functions,
Yeah.
they can be the things we just talked about, splines and stuff.
Absolutely. Each f can be estimated using, say, natural splines or smoothing splines or even local regression fits. You can even mix and match.
Mix and match.
Yeah. You could model one predictor with a natural spline, another with a smoothing spline, maybe leave a third predictor as just a simple linear term if you think its effect is straight, and even include categorical predictors as usual.
Wow, okay. That's incredibly flexible.
It really is. You can fit these models and even use things like ANOVA to compare models with different terms, say, comparing a linear fit for a variable versus a spline fit, to see if the nonlinearity significantly improves the model.
So you can formally test if the curve is necessary.
You can. And just like with polynomial regression, when interpreting GAMs, we often focus more on visualizing the shapes of those estimated functions, f1, f2, etc., rather than trying to interpret specific coefficients within them. The plots of these functions tell the story.
And does this work for, like, classification too? Predicting yes/no outcomes?
Yes, definitely. GAMs extend naturally to classification and other responses, just like regular linear models extend to logistic regression. For binary classification, the model would look something like log px, 1px, mere 0 plus f1x1 plus f2x2 plus mech. You're modeling the log odds as an additive combination of smooth functions.
Okay, GAMs sound like a really powerful and practical way to bring all this nonlinear modeling into real-world multi-predictor situations.
They absolutely are. A cornerstone of modern applied statistics.
What an amazing tour. Seriously. We started off just acknowledging that, straight lines often aren't enough because the world is curvy. We went from polynomials, the sort of simple curvy approach, to step functions with their blocky clarity, then the really smooth transitions of regression splines, the clever automation of smoothing splines, the focus of local regression, and finally, bringing it all together with GAM, letting us model multiple predictors with all this tailored flexibility.
The core benefit really across all these methods is empowering you, the analyst, to capture those complex patterns much more accurately, but doing it in a way where you still retain interpretability and have control over how complex the model gets.
Yeah, you're not just throwing data at a black box.
Yeah.
You're crafting a more nuanced model.
Exactly. So you should now have a really solid overview of how to build models that can better reflect the complex, nonlinear reality we often see in data, moving beyond just good enough approximations to something much more insightful.
It really feels like giving the data a better chance to tell its own story, not forcing it into a shape it doesn't fit.
Well said. And if we connect this back to the bigger picture, mastering these techniques for moving beyond strict linearity is, well, it's pretty much an indispensable tool for anyone doing serious statistical analysis today. It just opens up so many possibilities for richer insights and better predictions.
Definitely feels that way.
And it makes you wonder, doesn't it? It raises this question. Thinking about your own work, your own experience, given that real-world data is so rarely perfectly linear, what familiar problems or predictions that you deal with might actually benefit from one of these more flexible, nonlinear approaches?
That's a great question to ponder.
How might actually capturing those curves, those bends, those sudden shifts, how might that change the insights you draw or the decisions you make based on the data? Something definitely worth thinking about as you explore these powerful techniques further.